Colleagues of ISSI, dear all, it's my pleasure to welcome you to our second seminar here after the big break again in person. It's very nice to see you all. It seems that we are already in the summer. I hope it's not getting all too hot in here. Our guest today, our speaker today is Professor Thomas Schildknecht, and it's a special pleasure to have you because I heard that you had a very busy day today, because actually you may know that on the Ucht Sternwarte today there was the, I don't know what is Spatenstich, the start of construction of the new telescope, or it's more than a telescope actually. It's also a place for information on space, on research, but also on sustainability. And there was, the construction started just today. There was a celebration. So you came here, and from that I deduced that tonight actually you're going to travel again.
Yes.
Okay. So what you can already see from this little introduction is that Thomas is actually involved in a lot of activities. And to be more precise here, so I mean, he's really a world-known expert, I would say, in the science of space debris, space science, safety and sustainability. And you're working in that, I think, for 25 years or even longer. He is the director of another observatory, which is not too far from the Ucht, which is Zimmerwald. I hope you know it all, otherwise it's really worth going there. It's not only a very nice observatory, it also has a wonderful view on the Alps, and maybe also in winter, when we are poor and below the fog, then you can go up and you have a wonderful, wonderful view. So he's the director of that, and you're also the vice director of the Astronomical Institute, the IUP, at the University of Bern. But I think what is really special for you is that you're really a member of a lot of governing bodies in this context here. So because in this subject, maybe in comparison to, I don't know, extrasolar planets, there is of course also a very strong political side involved in this. And Thomas is, for example, in the ESA delegation, in the Interagency Space Debris Coordination Committee, which tries to find measures, to define measures to mitigate a little bit the dangers that can occur if there is too much space debris. I'm sure you're going to talk about that in a lot of details. He is also a member of the Swiss delegation in UNO, of the United Nations Commission on the Peaceful Utilization of Space, I think, which is also a very important body here. And he is the chair of the ESA Space, also for the European Space Agency. He's the chair of the committee which is advising the Director General on these matters. And I could go on for a very long time, but I think the floor is yours.
Thank you very much for the kind introduction. So I would like to give you today a briefing on this topic, which is a little bit different from what you're used to hear about, you know, frontiers in the universe or extrasolar planets or in other disciplines. So the reason why I came to this subject here, space debris, I'm going to tell you what space debris means, actually, is my former life, I would say, where I was searching for supernovae, minor planets, comets in the solar system. And in the late 80s, I was asked by an ESA member, because I was involved in a mission there, and we wanted to improve the orbit of that mission. And then by the end, I was asked if I could also observe some space debris. And yeah, of course I said. It was a bit naive because I had to prove that we could do that. And that was the start of my career as a space debris guy, which I'm still doing. I still have a group working on that. So some of the members are here. So what is space debris all about? If we look at the history, what I'm going to show you is the historical evolution of the near-Earth space environment. On the right-hand side, you see the low Earth or near-Earth environment. On the left-hand side, you always see a view from about 15 Earth radii. And the small dots here are the number of, or are the artificial objects at that given time in space. And in most cases, most of these objects are not active anymore. And if they're not of any use, purpose, we call them space debris. So this is 1965. You see we have a lot of dots in low Earth orbit. We already have some ones in higher orbit. 1970, you start seeing this ring of pearls here around the Earth at an altitude of roughly 36,000 kilometers, which is nothing else than the geostationary ring. If you put a satellite there at this altitude, you can manage to have the satellite in an Earth-fixed system always at the same point. And that's the whole purpose of these satellites in most cases. So on the lower Earth orbit already, it's like a beehive. If we go further here, 75, 1980, 1985, more and more in this geostationary region. And you also see some objects in highly eccentric orbits with an apogee mostly above the northern hemisphere. These are communication satellites for northern hemisphere areas because they stay a long time over the northern hemisphere, while the geo satellites are not worried, you know, if you are at 60, 70 degrees latitude, they would be almost at the horizon. So we needed to have some other systems, in particular Russian systems, because their territory is very far north. So 1990, 1995, 2000 keeps, you know, accumulating both of these environments, 2005, and it ends at 2010. Again, 95% of these dots are actually space debris. What do we know about space debris? Nowadays we know about 30,000 we know by name. And when I say by name, this means that we know their orbits, more or less. Not highly accurate in most cases, but we know something about their orbits. So these ones are all larger than about 10 centimeters. 35,000. From models and deep surveys, we know that there is at least 60,000 more of the size of, let's say, 5 centimeters and larger, and we go down to 1 centimeter. The number is roughly 900,000, or, you know, it could be 800,000, it could be 1 million, whatever. 1 centimeter, if you come up with the physics, these orbits here in low Earth orbit, we have velocities of 7 kilometers per second. Higher up, it's only 2 or 3 kilometers per second. But 7 kilometers per second, at that velocity, a piece of 1 centimeter of aluminum, for example, if it hits another object, has the energy or releases the energy of a hand grenade. And this is the real issue, why we care about these objects. You know, hand grenade on a satellite, not a good idea. Hand grenade on the International Space Station, not a good idea. So, we have models which are based on observations, which give us the 1 meter, the 10 centimeter, the 1 centimeter environment, and even the 1 millimeter environment, because the 1 millimeter environment could still be lethal for your satellite. I mean, if your satellite gets hit at the wrong position, or your central computer in the satellite gets hit by 1 millimeter debris, it could be lethal. So, this is the real reason why we care. Where do these objects stem from? I mean, the source is obvious. It's launches, and we put up there satellites, but with each launch we put more than the satellite. In most cases, we leave the upper stage up there. And if you have some residual fuel in the upper stage and you don't vent the fuel or burn the fuel to depletion, the fuel can ignite even decades decades after you left the upper stage. And this happens again and again. We have still about 10, we call them breakups per year. 10 breakups per year. More or less, you know, catastrophic ones. It could be small ones if a battery explodes in an abandoned satellite. That gives you a few dozen of pieces. If an upper stage explodes, that can produce hundreds and thousands of pieces of very different size. Okay, what are the indications that this is really a problem? If we look at our famous space station, for example, this is a historic image because it's the last mission of Endeavour, 2011. And what you see, why I put this image here, you see that the robotic arm of the shuttle here is inspecting the lower part of the shuttle, the heat tiles. And in the last missions, this took 2 days just to make sure that the heat tiles were prepared for the re-entry. And the main danger was, apart from during the launch, was space debris impact during the mission. Because, of course, the shuttle was positioned in a way in the ram direction so that the astronauts in the shuttle, for example, would be shielded by the heat shields. But if you need the heat shields for re-entry, this is a problem. At the same time, it's nice to see our European ATV docked here. This is the European. The European module is behind the shuttle. This is the Japanese Kibo module. If we look more closely at the space station, we see that this station is peppered with impact. It's really peppered. Just here you see this is a piece or 2 pieces of solar cells knocked out from a small space debris. This is a hole in one of the shields. The space station is heavily shielded for these type of impacts. Another one here, and what you see up there is a hole in the thermal insulation, which is about 5 centimeters in diameter. Luckily, you know, the piece who created that one was not penetrating the back wall. But the space station crew is prepared for, you know, the case when the back wall would be penetrated, and so that they could separate the individual compartments of the space station from each other in order to isolate the area where you have a hit. You could ask if this is not micrometeorites. From other, you know, samples which we brought back from space, we know that in the size range above about 10 micrometers, all the impactors are 90% or more are artificial objects, are space debris because of their composition. You know, if you find aluminum oxide, if you find aluminum, or if you find zinc, or all these kind of things are not, you would not expect them from micrometeorites. Below that, the environment is dominated by micrometeorites, no question about that. So, yeah, it even happens with active satellites. This is an example, Sentinel 1A, which some of my colleagues here are still using, it's still a very active satellite. 2016, a loss of power, the attitude was disturbed, and in retrospect, we could see that the orbit was even a little bit disturbed, and luckily we had a camera to look at the solar panels, and you see this part of the solar panel is heavily damaged. We know that this is from an impact of a particle of the size of a few millimeters in this particular case. So this was a wake-up call. You know, in February 2009, 10th of February 2009, we had a collision between an active satellite, an active Iridium communication satellite, and an abandoned Russian Cosmos satellite. This collision produced more than 2,000 objects which we could track, so objects larger than 10 centimeters, and many, many more smaller ones. And what I'm showing you here is that this cloud of debris is dispersing very, very quickly around the entire globe, and you end up with a shell of space debris after roughly 1 year. This is just orbital mechanics, nothing else, why this happens like this. So this is the real problem. These clouds don't stay together, so they spread over a large area. And even nowadays, this happened at a high altitude. Even nowadays, many of the satellite operators, including ISSI, are doing maneuvers on a regular basis to avoid collisions with these debris pieces. I can show you an observation we did in our observatory here in Bern, near Bern. What you see here is a video with the stars trailed and all these small dots here. It's peppered with small dots. These are fragments of, a breakup of an upper stage, which happened in 2019, and we observed that breakup, I think it was less than 24 hours after the fact. So why should we care? I already indicated why you should care, but it depends on who you are. You know, if you're a satellite operator, an owner, operator, you're concerned about the safety of flight, preventing collisions. Oh, I want to avoid that I'm going to collide with one of these objects. And in case you have an issue, a contingency, you want to know the cause. You know, is it the failure of one of my hardware component, or is it due to space debris, or something else even? Designers, of course, satellite designers, they want to know more about the risk, they want to do shielding, launch campaigns and so on and so forth. But governments, space agency and scientists, they're more concerned about preserving vital services. Like, for example, you know, what we all know is the example with navigation services, critical infrastructure services, but there's many, many more. You know, there's many of our infrastructures here on Earth depend on services in space, power grids. You know, usually we name also the banking systems because of the synchronization of the clocks and so on and so forth. Many, many more than you could imagine. Scientists are more concerned about the long-term sustainable use of space. Can we do space operations tomorrow, 10 years from now, 100 years from now? Can our kids go up there, you know, and enjoy, staying in a space station? Or is that becoming too dangerous? What is the evolution of all of that? So the science part of all of that is actually, we are asking a lot of questions. How many of these are up there? What's their size distribution, orbital regions? What's the nature of some of these objects? For some of the objects, we don't know even the nature, you know? Sources, sinks, physics, creation, evolution of orbit, long-term evolution of all of that. And finally, this is our approach. We search for debris, we survey the sky for debris, we determine their orbits, and finally we physically characterize the debris. And this is just one of the observatories we are using for that. This is our own observatory in Zimmerwald with quite some telescopes where we have optical telescopes, we do satellite laser ranging, and so on and so forth. And this is, again, not all of the sensors we are using, but we are using, on one hand, a 1 meter telescope owned by ISSI in Tenerife. We have our own telescopes here in Switzerland, a 1 meter telescope, an 80 centimeter, 2 times 40 centimeter, and that's the smallest baby there. This is only a 30 centimeter telescope. Most of them are, or some of them are exclusively used to search for space debris, uncharacterized space debris. We also have stations abroad. We have a small network together with the German space agency, the DLR, and one station is in South Africa. This is the outside view of that telescope, fully robotic. We have one in Australia, and we'll soon have one in Mexico, which we all use in fully robotic way to do space debris observations. We even use our own laser ranging system. This is the laser in Zimmerwald as well, to measure distances to space debris. This is very challenging because space debris are not equipped with retroreflectors. Usually all the satellites we are measuring with this laser, they're equipped with retros, so that some of the laser light is really coming back. Space debris don't have retros. It's much more difficult to get even a single photon back from one of these debris pieces. So what do we know? This is a picture of the official catalog at end of the year 2019. This is the official US catalog at that time. This was at the time where we had several breakups. And on the right-hand side, you see, on top of this official catalog, you see in green, this is what we, together with Russian colleagues, came up in terms of breakup fragments. You see, there's 3 breakup fragment classes here, 3 distinct orbits. And again, this is one of these movies where you see the dots here, all fragments from 1 breakup. This is the mother object here, an upper stage, which probably was not fully depleted, so had some residual fuel. I think this is nothing new. So we are looking for these small-sized debris, and what I'm showing you here is what we found over the years in the geostationary ring. So this ring where you have satellites, which some of them are stationary. The red bars are the objects which we didn't know before, which are not in the catalog. This is astronomical magnitude, so right-hand side is faint, this is bright, but more interestingly, I put here an indication on the size, 10 centimeter, 15, 40, 60. So what you see here is an entire population of fragments, space debris, between, let's say, half a meter size down to 10 centimeters, which was not known before. So, we don't know the events which produce these populations. And the fall off here on the right-hand side, by the way, is fully due to the sensitivity limit of our sensors. So it's not the population. The population is probably going up there. So, we had a closer look at them. This is now a diagram which is in orbital element space. I don't want to bother you too much with that, but on the x-axis you have the mean rotation or the mean motion in revolutions per day. So here we have the geostationary ring, it's 1 revolution per day. And here we have the eccentricity of the orbit, shape of the orbit. In blue, these are the objects in the catalogs which we know, and this entire region, no parent objects there, so why should we have debris pieces there? This was a big mystery 15 years ago when we discovered that one. So we followed some of these objects over time, and this was the result here. This was the result. Over time, we have seen that, the mean motion is staying the same, not surprisingly, because that's physics. But the eccentricity is going up and down and up and down with roughly a period of 1 year. Again, mystery. What is causing that? Which type of orbital perturbation could cause that? And we went ahead and improved these orbits and tried to estimate some additional parameters, and one of them is what we call the area to mass ratio. So the ratio between the size of the object and the mass. And believe me or not, the area to mass ratio of these objects here was like crazy, was like 10 square meters per kilogram, 15, 20 square meters per kilogram. And this is, a piece of paper here, normal type of paper, not this one, is about roughly 8 to 12 square meters per kilogram. So these things here are even more lightweight than the pieces of paper. So it became clear the reason why they they do this dance up and down is solar radiation pressure. We can explain that if we have these type of light white objects. Of course, we speculated immediately, hypothesized that this would be multi-layer insulation material, you know, that these blankets which cover the satellites to protect them from heat and cold. But we needed to know more about that. So what do? We characterize these objects. And one type of characterization is we look at the temporal variation of the brightness. And what you see here is nothing else than this is brightness, faint, bright on the top over time. And we see how these objects are varying in brightness. And from, you know, astronomical techniques, we are used to use these light curves to estimate shapes and attitude motion. So, you know, if you would have pieces like pieces of MLI or solar cells, for example, and if we rotate these devices, sometimes they would be bright, sometimes they would be dark, and you know, we do the same thing for asteroids. This is, on the right-hand side is a light curve of an asteroid, and we know how to infer the shape from these light curves. But space debris objects are much more complicated, so to come up with spin rate, spin axis, shape is very, very difficult. This is an example here of of such an observation, and you see it's flashing. This one is an abandoned GLONASS satellite. It's a large satellite, but at 20,000 kilometers distance. And this is the kind of information we use to infer attitude motion. If we use laser, we can do something similar. This is a European satellite which failed. This is Envisat here, and we measured Envisat and still do with our laser ranging system. And the idea is that we now measure not the brightness variation, but the variation of the distance to some of these specular reflecting points on the satellite. In this particular case, it's the retroreflector, and you see how the distance is varying. From that variation, we can infer or even determine the attitude motion of this satellite, which we did. Why is that of interest? Because, you know, we should not leave that object up there. And if you want to catch it, you need to know perfectly its attitude motion. Otherwise, you will never be able to catch it. And even before you design your catcher satellite, you need to know that motion. Our high error to mass ratio objects. If you want to know more about the material type, we have to go ahead and measure colors or even spectra. And we do that and did it. One of our telescopes, the 80 centimeter telescopes, we once in a while equip that one with a spectrograph, so we can measure spectra, reflection spectra. It's not the same thing as spectra from stars. In principle, what you see is the spectrum of the sun reflected by the satellite, or by these space debris pieces, but it's not perfectly the solar spectrum because, you know, your space debris has some reflection properties, and these properties we want to know. Okay, so we did spectroscopy of some of these pieces here. This is one example. This is wavelengths here in angstroms. So this is blue, this is red, and this is the intensity of the reflection we got. This is a very telltale feature here. It's a knee at about 500 nanometers. We didn't see that in any other observations than in these higher to mass ratio objects. And if you compare that with lab spectrum, this is a lab spectrum we have taken here from MLI. MLI, these are very thin foils, multi-layer insulation foils Often one side is goldish, the space-facing side, the other side is silverish, and you see that knee here. We have been measuring a lot of other materials in the lab, you know, well, aluminum, some paints, solar cells. None of them has that knee here. So we are pretty sure what we are seeing here is multi-layer insulation material. Very important, because if we can tell satellite, you know, designers, hey, you have an issue with this MLI because it's peeling off after a certain time in space, yeah, we can perhaps do something about it. So let's have a look at the evolution of all of that. So this is the evolution of over time of the known objects, of the ones we know by name. So yeah, steadily evolution here, and we have some step functions here. They're all, you can attribute them, for example, to the Iridium Cosmos collision. That one we can attribute to something else. This was a Chinese anti-satellite test. Not a good idea to do that at the altitude they did it. But what we see in particular is in recent years, these numbers have been raising exponentially. One reason for that, apart from the mutual collision between these debris, one reason for that is this here. This is the launch traffic in terms of number of objects launched. And, you know, that was an average number over the years, about 100 launches, 1 up to 2 satellites per launch. But during the recent years, you know, this is a huge increase. We have been launching during 1 year as many satellites as in the entire time before. So these are launches of commercial satellites. All the yellow bars here are commercial satellites. You know these type of satellites, you know Starlink from Elon Musk and other ones. Small, relatively small size satellites. So, if we go ahead and model now what could happen because of mutual collisions between the space debris, the uncontrolled space debris, the situation looks somehow like this one. This is a simulation from ISSI, and it's barely visible, but each time you have a flash, this is a collision, more than one per decade, producing each one thousands of fragments, and you see this is an exponential cascading effect here, which is really not what we should allow, you know, to happen in this environment. So in numbers here, again a simulation, this is before these mega constellations, thousands of satellites which are launched currently. Before that, there were simulations, and in the black curve here shows you over the coming 200 years the cumulative number of catastrophic collisions. Catastrophic collisions means a collision between two relatively large objects which results in the destruction, full destruction of the two objects. Usually this is happening if one of the partners or of the in the collision is of the order of 10 centimeters and larger. So what's happening is an exponential rise. And then we have different curves here where, you know, we have different measures of what we call post-mission disposal, which means nothing else than that after the end of the mission, you should make sure that you take out the object of the environment. We call that post-mission disposal. The best way of doing it is let the object, you know, enter the atmosphere, and in most cases then it burns up completely. But you see, even if we have 90% post-mission disposal with the traffic rate of 5 years ago, we still have an increase in the number of collisions. So, not really nice. The current compliance to, you know, guidelines to do post-mission disposal is extremely low. In low Earth orbit, we could say more or less, you know, 20% of the objects which should have been doing a post-mission disposal tried to do one or did something. And if you look at the success rate, it's even much, much lower. So we really have an issue here. But this is the really scary, upcoming, and the new world in space. It's already there. What I'm showing you is one of these constellations, which are currently put into place. And, the one you know best probably is SpaceX, the current Starlink megaconstellation, as we call it. We have more than 2 days ago was the last launch, on the 6th of May, actually, each time 53 last time launched together of these satellites. So we have roughly 2,500 objects from that constellation already deployed. There's other ones on the horizon. There's OneWeb, which already deployed quite a few, 430 roughly. There's Kuiper, from Jeff Bezos, Amazon. They want to launch 3,000. And there's other ones. There's the Chinese, which announced a constellation of 30,000. And there's one guy which filed for licenses for 150,000 satellites. Even if a small portion of that is going to be realized, this is going to create really serious problems. So, what are the risks and challenges here? So, first of all, we have that existing space debris environment, which is already challenging. We are having collisions among space debris, which we cannot control. Even if we would know all the orbits of all the space debris, if two large upper stages would be on a collision trajectory, we could just watch and enjoy the show. Right now, we have no means to prevent that. So we have collisions involving active spacecrafts or potential collisions or even crewed spacecraft. There we can do something. Active versus active, we can do collision avoidance maneuvers. Active versus space debris, we can do collision avoidance maneuvers. But yeah, we have several breakups, several per year, as I mentioned. We have mission-related debris still. We have upper stages we leave up there. We have adapters which we leave up there. The European Vega launcher is still regularly leaving an adapter up there, which is not nice. We have to make sure that at least the Ariane 6 is not going to leave upper stages up there, and so on and so forth. Just mentioning the European challenges. And we have debris released from aging spacecraft. Clear indication. What are the technical measures to, counteract this evolution here? So technically, of course, we can prevent collisions, and that's where most of the effort goes in today. And I will show you that this is not going to save us or save the world. This requires space traffic coordination, space traffic management. We need to observe all these objects. We need modeling theory, algorithms to be improved to make this collision avoidance effort efficient. Leave no trace is one measure, so it means post-mission disposal. Really don't leave anything up there. Right now we have this rule of, you should not leave your asset for more than 25 years after the end of the mission. It's crazy. We have to reduce that number, and we have to make sure if you dispose your asset in your satellite in the atmosphere, that it is designed for demise, that nothing, survives the re-entry and reaches ground, because that would be a danger on ground. So we need really to make sure that we prevent breakups. Passivation, safe design should be a must, and because the European Ariane upper stages were notoriously exploding in the 80s of the last century, when passivation measures were implemented, none of the upper stages of the Ariane 4 upper stages, none of the Ariane 5 upper stages ever exploded again. So it's efficient. We can do something about it. And we have to reduce the risk from the existing space debris population. And yeah, for example, if we have two upper stages on a collision course, we have to do some just-in-time collision avoidance, as we call it. Any kind of measure to move, nudge one of these two pieces a little bit so that it's not going to collide. A little bit, you know, a few meters perhaps, using ground-based lasers or whatever you could think of, you know, requires very, very sophisticated space traffic management. Active debris removal, we can remove objects actively. We can service objects, in-orbit servicing, to re-establish the maneuverability, for example. This has been, you know, this has been shown in 2 cases in the geostationary ring to extend life, and we need perhaps to remove small-sized debris. This is just, one of the demonstration mission, the ISSI ADRIOS mission, active debris removal and in-orbit servicing mission, currently led by a Swiss startup company, ClearSpace. This mission should remove an adapter of the Vega, European Vega launcher in the year 25, more likely 26, as I know they have some delays right now. So this is just an example of active debris removal. Of course, these challenges have to be addressed at an international level. You know, it's like in the climate discussion, or let's say the global warming. We can do the best somewhere in Switzerland, and we don't do the best, by the way, in terms of CO2 emission, but if we would, that would not save the world, as long as that, you know, other big nations would not reduce their CO2 emission, as an example. And the same is true in space. You know, we need to agree on some measures at the international level. And this is, again, very, very challenging. It's comparable to the challenges in the global warming and climate discussion, because the same kind of arguments, you know, come up here as well. You know, that there's economical interests, there's strategic interests, many others, and on top of that, in space, we have military interests. So we still face the issue that space is a very important military asset for many nations. So there are a lot of efforts, still are a lot of efforts at the international level. And just to name a few, in 2005, the Space Debris Mitigation Guidelines were of the Interagency Debris Coordination Committee, which came up with its own guidelines in the late 90s, were adopted by the UN. So we have UN-adopted mitigation guidelines. These are high-level guidelines in the sense of don't pollute, more or less, or do post-mission disposal. They're not telling you what exactly you have to do. That's something which has to be implemented at national level. Because, you know, finally at the UN or international level, the individual states or nations are responsible for whatever their actors are doing in space. Switzerland would be responsible for, you know, whatever Swiss actors would do in space. So, yes, we had the UN Space Debris Mitigation Guidelines, which are designed along the IADC guidelines. We then had several attempts. We had a European Union draft International Code of Conduct in outer space activities. That one is, yeah, not anymore pursued. And this one is an interesting one. I mean, it took us 8 years in the UN Committee for Peaceful Use of Outer Space to come up with guidelines on the sustainability, long-term sustainability of outer space activities. 21 guidelines. And I was member of the Swiss delegation, and some of the guidelines are Swiss guidelines, which we initiated. Of course, they're not Swiss, these are UN guidelines, but I could show you some of them. The working group, yeah, there's a new working group which should work on continuing that effort in coming up with guidelines. It's becoming increasingly difficult because of political reasons, you know, that during the past years, some states deemed, how should I say, deemed multilateral or international deliberations not anymore useful, or didn't want to enter multilateral discussions, and we were really stuck here for some years. Now we have the working group, but yeah, let's see how this is going to evolve. All these guidelines are non-binding. These are not laws in the sense they're not binding, but nevertheless, you know, if states sign these non-guiding guidelines, there is a certain obligation to do it, and they take it seriously. So what are the challenges? I already mentioned some of them. So megaconstellations are right now monopolizing some of these regions. So until now, you know, even in the geostationary ring, there were roughly as much space as demand. So we could still assign slots. The ITU is assigning these slots. International Telecommunication Union via the frequency regulation, and was still more or less okay. But now, you know, if we have a Starlink constellation deployed in a certain altitude shell, you know, at a certain point in time, this shell is simply full, given the current technical means we have to orbit determination, precision or accuracy of these orbits, collision avoidance measures, and so on and so forth. So it's a first come, first served right now. It's like in the gold rush, you know, you go there and this is my claim. Although it's not, nobody's going to say this is my region, but just by the fact that you filled up the region, oh, sorry, it's now full. So we have that very serious problem here, and in principle, we need to address that at the international level. I mean, we have to decide, are we going to assign different slots to different operators, nations, on what, you know, based on what criteria? Is there good missions, bad missions? Finally, we'll have to decide, or the community has to decide, you know. You know, if somebody would put up there 1,000 satellites for advertisement, I don't know, advertising a product, polluting the night sky, you know, for example, is that something we should ban, not allow? Can we do that as a single nation? No, we can't do that. Can we do that at UN level? What would be the criteria? I just don't know, and we have not been addressing this problem. Then we have, nowadays we have a lot of rendezvous and proximity operations. They always have some risks. We have no rule, for example, for announcing them. So currently there's a lot of operations going on in space where you have one spacecraft approaching another, not yours, from another nation, and obviously, you know, the other gets nervous for many reasons, you know. First of all, who is this guy going to collide with me? In most cases, this is not the real issue why you get nervous, but you get nervous because you think, yeah, this is an inspector spacecraft who wants to know more about me, or it could even be a weapon. So we need rules. Active debris removal, same thing. We need rules. You know, can I just go up there and take somebody's debris piece? No, I can't. We need rules on the of the road. I mean, we have that in the air and on sea. I mean, there's clear rules. How do you announce at sea if you approach some other ships? Even, you know, the military domain, there's rules to make sure that there is no misunderstanding. And we have a lot of sensitive political issues. The gray zone between safety and security. So the gray zone between pure safety of your mission and the military aspects of sharing of orbital information. Even we cannot even share most of the orbital information because there is this military classification schemes. There are still, you know, objects out there which do not exist. How to involve private actors? Because states are responsible. It's still states at the international level. But, you know, nowadays, the evolution is driven by private actors. Should we come up, bottom up with these rules? You know, should the private actors in you know, industry associations coming up with rules, or should we do it top down from the UN? And I know what you're going to tell me. Yeah, if we wait for the UN, it's going to take ages. True. But if you leave that up to a bunch of US companies to come up with the rules, we have a problem as well, because we have to get the Chinese on board, we have to get the Russians on board, we have to get the Indians on board. Otherwise, you know, you can come up with rules as much as you want. So bottom up versus top down. My point is here, we need both. We need everything here. We need all measures we can. Okay. We need a global collaboration, and now I'm back and with my hat as a scientist. All our measurements we do, don't make any sense if we don't share it with our global partners, and we have many of them. I just mentioned a few. You know, ISSI is our key partner, the Germans, JAXA, the Japanese. We have several partners in Russia where we have difficulties, of course, right now to share the data. The Kalish Institute of Applied Mathematics in Moscow is one of our prime partners. And many others. So, what are the take-home messages here? The take-home messages are, we need international collaborative and holistic approach to address the space debris issue. Really a holistic approach. We cannot just do collision avoidance or remove one object from space. That's not going to save the environment. And what we are doing here in the research part, we really provide the scientific foundation for a sustainable use, because we, you know, can give you hard numbers. What would be most efficient? What's the problem out there right now? And with that, thank you for your time.
Thank you very much for this very interesting, but at the same time also a little bit scaring talk with this perspective. Questions, please. Yeah, here in the front.
Congratulations, it's very nice to see you again.
Thank you.
You made a computation of how long the space will be dead completely because of what you analyzed. And, is there any projection of how long the situation that we have today will continue?
Yeah, we do these kind of evolutionary scenarios. We projecting forward. It very much depends on the traffic model, and this is the point, you know. Who could have guessed 5 years ago that we are going to have a Starlink constellations, you know, 2,500 objects launched by one private company within 2 years. Unbelievable. And I don't know if any of these 10,000, 20, 30,000 constellations will become reality. So this is the big unknown in the game. We know that in certain regions, this is the altitude region between about 700 and 900 kilometers, the density of space debris pieces is about at the limit for this, cascading effect of the Kessler syndrome, of exponential rise in number of pieces. And we think we see that. I'm most concerned about the several hundred upper stages in that region, upper stages of 10 meters and masses of 8 tons. If some of these collide, and it's only a matter of time, they will collide once in a while, that will really change the situation a lot. So I cannot give you a simple answer, it's going to hold for the next 50 years or 10 years. I would say, even if I gave you a very dramatic picture here, I think we still have some time. We should act now, for sure, but it's not hopeless. I mean, we can do something against it, and we can do things better than we did before. And I have to say here, it's not bad will why we did it as we did, because we did it this way. It is so difficult, to go up there. It's so difficult to survive with your satellite in this harsh environment. So it's absolutely logical that you first had to master these things, to bring up your satellites, have them surviving for a certain amount of time before, you were caring about, bringing them back and not leaving a trace up there. I'm sorry.
There was another question here.
How long do objects stay in their orbit depending
on the altitude? Yeah, very good question, yes. Fortunately, in low Earth orbit, there is a cleaning effect, which is nothing else than the air drag from the remaining molecules, air molecules and atoms it's nothing else than the upper atmosphere. So if you go, let's say, to an altitude of 500 kilometers, it's just a bit above the space station, you are pretty safe in the sense these objects will come down in a few years. And this is the good thing about the Starlink constellation. They wanted to originally put that constellation at 1,200 kilometers. It was not a good idea. So if one of their birds, dies, it will still come down within, less than 5 or 10 years. That depends a little bit on the air to mass ratio again. If you go further up, at about 700 kilometers, you're at the limit of the 25 years rule. So it takes more than 25 years at that altitude. And at the 1,000 kilometer altitude, we are talking about 100 or even hundreds of years. In the geo ring, that's forever. There we have a different challenge. Bringing back these birds from the geo is taking so much energy that we currently use what we call graveyard orbits. We put them up by about 500 kilometers, at least that's the recommendation, above the geo ring, just to clear that very, very important region of space from dead satellites. So that depends very much on the altitude. And also on something which is very difficult to predict as well, and it's the solar cycle, the strength of the solar cycle, because the atmosphere, is blowed up during a strong solar cycle. You have more air drag at a certain altitude if you have strong solar activity, and it's hard to predict that. So these models, the evolution model, take that into account, but they have to come up with a model for the future solar cycles.
The back.
One of the very first satellites that was shot up was the ECHO satellite, a big sphere, aluminized, I think, blown up. And I think it was 1,000 kilometers. Is it still there?
No, this one is not anymore there. Yeah, but I know what you mean. It was a balloon-like, it was a balloon in principle, yes. There's some debris up there still at this altitude, which we think is from this, originating from this satellite. Because some of the debris was not having too high air to mass ratio, and that could have survived. So we have some debris up there which we attribute to some of these satellites.
With your analyses of the composition of, or the range of compositions of the material up there, does that suggest that it would also be useful to start using different parts of the electromagnetic spectrum to try to detect objects? Is optical still the best tracer?
No. You're absolutely right. Very good comment or question. For sure. I mean, the optical is not the best tracer for all these materials. We would like to see more into the infrared. We are using some infrared, and we have some measurements in the mid-infrared from other telescopes. You're absolutely right. It would make sense to extend the range to even up to 5 microns, because some of the materials have very specific characteristics in the infrared, for sure. There's other techniques which were named a lot. For example, polarization. The picture is a different one. You know, polarization measurements in astronomy are notoriously difficult, and all the experiments which have been done with space debris came up with the conclusion polarization is not giving you any information. So we couldn't see any particular polarization features for space debris. But for sure, infrared.
Please.
Thank you. I'm thinking now, because I'm really touched by these pictures. It's very nice. Thank you very much. I'm thinking about space taxis. So everybody is using a device which is actually attached to one of these actions should pay some taxes. You could just bring up a yearly budget and then divide by the people using one of these services. What do you think of that?
Yeah, thank you. It's one of many of these ideas. Yes, I agree. You know, the question is, how can we, how can we incentivize on one hand good behavior, or penalize, or make sure that we have the money to clean up the environment? And one idea, of course, would be that you would have to pay a tax, which, if you behave well, for example, you will get it back. If you take out your object from the environment, you would get it back. It could be via insurance companies. You know, we have been talking to insurance companies. The point is simply that many of these objects are not insured. These are mostly the objects in GEO, the large communication satellites, TV satellites in GEO, which are insured. And insurance companies are closely watching the situation and perhaps come up with incentives for good behavior. But the point is, again, I mean, if you are doing that in your particular country, if we would set up this kind of tax in Switzerland, nobody would probably come to Switzerland to get a license, because you can go to the UK without that constraint. The UK, for a certain amount in time, they were requiring an insurance to get a license to launch under UK law. They stopped that because it was detrimental for their own, economy. So how would you come up with something like this? It probably would have to be international, so that we have an international fee. Everybody has to pay the fee. Who is going to manage that? Who is going to use the money for what? And so on and so forth. The other point would be incentives, that you would have a benefit as a private company if you behave well. One way of doing this is probably not the best one, but is naming and shaming. Currently, Starlink, for example, they changed some of their designs and some of their mission profiles in order to be less visible for the naked eye. Because there were a lot of complaints, hey, we have all these bright dots in the sky, so this is light pollution. And they were doing it. Why? They don't want to be the bad guys. because if they're the bad guys, they get difficulties to get investors, you know, or risk capital and so on and so forth. So there is means like that. For example, right now, together with the World Economic Forum, a group of a consortium developed a sustainability rating, which is like what you have on your fridge. You know, you have AAA or AA or A or B, C, D. So a rating for good behavior. Why not? You have the risk of greenwashing in this particular case. Perhaps you're just greenwashing some of the companies by giving them a good label. There's other indices which are developed, like capacity indices, to have numbers when we reach the maximum capacity of a certain region in space, and we could think of, not allowing any more launches in that region if we think the capacity is reached. Again, who is going to play the police there? So currently most of the hopes are for incentives, not penalties, because we don't know who would be the act as police.
Reminds me a little bit of discussions we had in Switzerland about the behavior of some banks.
Right.
Experience here, I think. There was another question.
It's along the same line, actually, I would say. At a certain point, the companies themselves will feel the pain of launching another thing. They bring their own system into risk. They put it at risk. I mean, they see there's a certain saturation.
Yes.
And then they can't launch anymore. And at a certain point, they have to collaborate with everybody. And I mean, if they don't get any access to research or to common global research of that, I mean, they cannot be supported anymore. And for them, I mean, I think there's a break-even point when it is too risky, too costly to launch more into the same orbits. And I mean, it still has to pay off. I think it just, the regulation, I fear, will only be the money. For them. At a certain point, there's.
That's true. That's true. On the long term, you're right.
Still, I mean, there has to be something they have to know before. And they will probably couple via their own budget. And I mean, the more you comply with regulation, the more access and help you get, getting a kind of sensible distribution or help, being more sustainable.
That's true. In principle.
Feel the pain. I mean, they.
But the problem is the feedback, you know, the problem is the feedback cycle and the time scales, you know. I mean, time scales for a private company are of the order of, you know, return on investment is usually after 2-3 years maximum for the risk, you know, capital, venture capital. So if your time scale is 2-3 years, you don't care too much about long-term sustainability. If your time scale is like Elon Musk's, probably much longer for his constellation, you are perhaps concerned about getting licenses for the next bunch of satellites to be launched. So we have a lever there, you know. If you don't behave as you should, you don't get the next license in the United States. So you can then go shopping and see if you get one in the UK or...
Invest in collaborations who help you to optimize your strategy. I mean, this must be the idea of these companies, to optimize and then collaborate. And then might be, maybe this is too naive. It could pay off in the long run.
Yeah. That depends a little bit on your business model. I mean, some of the Swiss companies are keen to join, you know, this leave no trace initiatives and so on.
This is one like this clear space, and part of a big launch company should be kind of dedicated. Part of the money should be dedicated to this cleaning business. That makes sense.
Yeah. I agree, but it's not happening, of course, because nobody is going to pay for, you know, removing objects which have not been put there by the ones who have to pay. So in principle, for what's up there, mostly states would have to pay for. Yeah.
There was another question.
Yeah, it's same question again. I mean, who is paying now for the rendezvous and the proximity operations? I think the space agency and their members will pay that. So actually there would be a possibility to jump on or just to have a look at. I mean, these are numbers which should be known.
Yeah, these are numbers which are, let's say, investigated by many, many private actors right now as we speak. There's different opinions, you know. I mean, ClearSpace is seeing a market in some of the, not the active debris removal, but perhaps a real market in in-orbit servicing. There's others which see a market there. It's difficult to say, you know. The point is that there's only 2 examples where somebody was willing to spend dozens of millions to have his active spacecraft serviced. And these were large spacecraft in GEO. And there I see a market to extend the life of these large communication spacecraft, which usually have a lifetime of 10, 15, even 20 years. And if you can, you know, enlarge the lifetime by 5 years by having somebody, you know, servicing your spacecraft, docking and replacing the bus and the power system and everything for, or the attitude control system, station keeping system, that might pay off because these companies, you know, each month you can prolong the lifetime is worth millions. So that can pay off. But it doesn't pay off for a Starlink satellite. Because, you know, it's like with your smartphone. After 5 years or whatever, hey, would you like to have a service, a new battery on your smartphone? Some of us do, but most of us would not because it's old-fashioned technology. The new smartphone is 10 times smarter than the old one. So, or computer. And this is the main issue I see. I mean, I'm very skeptical concerning this in-orbit servicing market. If it's really a business case, I see some business cases, but in many cases I don't see that. I might be too pessimistic in this respect. I'm talking to many private actors to try to understand, you know, what I'm missing there, what I'm missing. But you're right. I mean, if there's a business case for active debris removal, we should do active debris removal by the private ones, you know.
Yes, over there.
So, Thomas, first it was a very nice presentation. As I'm a newcomer to the field, so first it's a comment. The last 3 solar cycles, we actually know that they are not typical ones, at least looking at the sunspot numbers or whatever characteristics. So we do not know how they are going to affect, especially those megaconstellations, if we get something more close to normal. And actually my question, just listening to you, are there any considerations in the community or models what happens in case of Carrington type event?
Yeah, there is some considerations, of course. There's 2 things which a Carrington event, 2 impacts of a Carrington event in space. First of all, many of the active satellites will have serious issues and will, you know, it could be lethal for many of the active satellites. That's one problem, you know. You end up with, I don't know, a good portion of the active satellites being dead after such an event. And the second thing is, it's less of a real problem, but we had several times massive events which blew up the Earth's atmosphere, and we have been seeing that within a week or 2, we lost a good portion of the satellites, or track of a good portion of the low Earth orbiting satellites because of that massive disturbance on the orbit because of, you know, the completely different air drag acting from one moment to the other. Really, we lost. I mean, you can look at the catalog. After such events, the catalog, 30% of the objects lost. That's another point. nowadays it might be less of a or less critical. We have more sensors out there. There's private radars out there right now. They do a very, very good job. But I would be most concerned by, having the lethal dose for many of the satellites out there, especially the ones, Starlink, that model, the business model is based on mass production, standard hardware, of course, space proven to a certain extent, but it's not anymore that space proven hardware we used to deal with, the years before. The idea is simply have redundancy, I mean, if one fails, I have 500 other ones which are up there. And that model is, fundamentally contradicting the sustainability and has a fundamental issue with events like a Carrington, for example. I don't want to say that the Starlinks will be all dead after a Carrington, but there is a certain risk.
Is there another question? Yes, please.
Are space debris also tracked, or is it planned to track them from space itself?
Yes, very good question, thank you. Yes, they are tracked from space themselves. So there is optical telescopes out there which are tracking space objects in general, not just space debris, but in particular also the active ones. In LEO, there's several ones. There's also optical payloads in GEO, which are doing these kind of observations. All these payloads are military ones, so we don't have too much information how well they, operate. But clearly, we should do space-based monitoring. And I'm advocating that for many years now at ISSI level. We have been doing studies, 15 years ago we have been doing a study for a space-based optical payload, small, 20 centimeter size telescope, to do two things. First of all, look at larger pieces in greater distances, but then also investigate the small size environment, millimeters to centimeters, where we have no direct measurements. So we could look at them because we are, the point is simply you could look at them in much less distance, at the ones in 5, 10, 100 kilometers distance. While if you do that from ground, the minimum distance is always of the order of 3, 4, 500 kilometers. But that's, yeah.
I think in the interest of time, this is probably the last question. I would also have many more, but Thomas, do you have time to join us for the apéro, or do you need to run?
I have, some minutes. Then I need to run.
This will be a short one. So I forget what exactly the term was which you used, but it was something like last-minute evasive maneuvers or something like that. I'm just wondering how last minute is it? What is the typical time scale? Is it hours, days?
Yeah, it is just-in-time collision avoidance I was mentioning, yes. I mean, for let's say, active collision avoidance, an active spacecraft and inactive or active, currently the time we need to plan these maneuvers and execute the maneuvers, depending on the satellite, are of the order of 1 day only nowadays. There used to be several days to upload commands and make sure that everything is nice. But nowadays it's 1 day perhaps. But there's operators which claim that they're able now to do these kind of operations within an orbit, 90 minutes or half of the orbit. So the shorter this time frame would be, the less of a maneuver you need to do. And the other point is, how well do you know the trajectories of the two pieces? If you know the trajectories to 5 meters, you just need to move a few meters and you are safe. But if you know them only to 100 meters, you have to move a lot. And this just-in-time collision avoidance, that depends very much on the accuracy of the orbits you have. I'm assuming that you should have accuracies of the order of much better than 100 meters, let's say 10 meters. And if you come within the hard body radius of these objects, We would need with nowadays, let's say with the ideas we have, for example, powerful lasers, which do ablate some of the material so that we could move one of the stages a little bit. We would probably need something of the order of a few days and several laser ranging stations or laser stations to be engaged to move an upper stage enough, which means to move it by several 10 meters. But again, it depends on the accuracy of the orbits you have at hand. Would be okay, you know, if we can predict the orbits well enough over a week, for example.
But we will need a laser a little bit more powerful than the one we have in Zimmer.
Much more powerful. Yes. We are talking about lasers which are of the orders of kilowatts. And the point there is simply, you know, this type of a laser, they exist, and you need adaptive optics and a lot of things, you know, to focus the laser up there. But the issue with these kind of lasers is simply these lasers are weapons. So how do you regulate that? Would you allow to develop a country such type of lasers?
I remember I once had my finger in the laser up at Zimmerwald. Experience. So maybe, Thomas, thank you very, very much. I think there are many more questions. Let's go down and continue the discussion there. Thank you very much.